Hey, what are you still doing here? Oh, you're waiting for your Dogonomics merge to arrive. I see. Well, since you're here, we might as well go over some proofs for 388, right? Would that make you feel better? It's a nice little family activity. You know, sit around the fire, watch some 388 proofs. I like it. All right, well, let's just start with our OLS estimators, okay? Yeah, let's do the math for that. We know that OLS, you know, in the bivariate case, we want to minimize the sum of our squared residuals. Okay, that's how we choose our OLS estimators. We want to choose B0 and B1 to do that. So let's go ahead and do it. Okay, what's a residual? It's going to be yi minus y hat. And what's y hat? Well, it's B0 plus B1x. Right, that's our line. So let's just put that in here. B0 and B1xi. All right. So that's the sum of our squared residuals we're going to minimize. And let's do it. How do we minimize? We take a first order condition, right? Take the derivative, set it equal to 0. So let's do it. Let's do it with B0 first. All right, derivative with respect to B0. And let's see what we get. Well, you know what I'm going to do? Actually, I'm going to minimize the average of my squared residuals. Is that okay? I think the 1 over n is just going to make it a little simpler, and it gives you the same answer either way. So let's do that. Okay, I'll keep the 1 over n there. And I'm going to do the sum, my squared residuals, and the derivative. So my 2 comes down here. It's a sum, so I got the 2 in there. But then, you know, minus, because there's minus B0 in there. So negative 2 yi minus B0 minus B1xi. Okay, and that's what I got. And set that equal to 0. When I set it equal to 0, these are officially my OLS estimators. B0 hat and B1 hat. I just have to find out, just got to solve for B0 hat right there. So we got 1 over n, and I don't think I want that negative 2, so I'll just take it out, right? There's a 0 over there, I can do that. So let me distribute this sum. I got the 1 over n, I got the sum of my yi's minus the sum of my b hat naughts minus the sum of my b hat 1 xi's, all equals 0. Well, 1 over n sum of my yi's, that is literally just y bar, right? So that's a y bar. Okay, this is indexed by I. B hat naught doesn't depend on I, but it's basically like, you know, it's I to n, so it's b hat naught summed n times. So I got n b hat naught, but then 1 over n, that just gives me b hat naught, right? All right, well, b hat naught then, and then minus, and again, I can pull that b hat 1 out, and I get 1 over n, sum of my xi's, that's just x bar, right? So I think that's what that's going to turn into. And oh yeah, I'm solving for b naught, so I guess I'll get b hat naught equals y bar minus b hat 1 x bar. All right, well, that's pretty simple. Pretty simple, kind of fun actually. All right, so let's do it for b1 right now. Derivative with respect to b1. Let's see. Let's keep that 1 over n again. We're going to sum. I'm going to bring down my 2 again, and it's also going to be negative. But now we got an xi in there, so this is negative 2 xi times yi minus b0 minus b1 xi. Okay, and set that equal to 0. Now these are official OLS estimators. Now I got 1 over n. Let me see what we got. I don't think I want the negative 2 again, so I'll scratch that out. So we got the sum of let me multiply this. So we got xiyi minus the sum of my xi b hat naught minus the sum of my, xi b hat 1. So what is that? Xi squared b hat 1, okay, equals 0. All right, let's see if I can clean this up a bit. So 1 over n, sum of my xi yi, I think I'll just leave it like that. 1 over n, sum xi yi, minus, sum of my xi b hat naught. I'm going to plug in for b hat naught, because we know what that is. That's y bar minus b1, b hat 1 x bar. So this is minus the sum of xi and then b hat naught, which is y bar minus b hat 1 x bar. Okay, so let's work with that. I'm distributing my 1 over n, aren't I? So I'm just going to put that everywhere. And then I got, what is that, minus 1 over n, the sum of my xi squared b hat 1. Okay. I like it, and of course, it all equals 0. So now, what do I get? 1 over n, some xi, yi, still leaving that like that, right? Minus 1 over n, the sum of my xi, y bar, and, plus 1 over n, the sum of my xi, x bar, b hat 1. Am I doing that right? Xi, x bar, b hat 1. Let's say I'm doing that right. And then minus 1 over n, the sum of my xi squared, b hat 1. I can actually pull the b hat 1 out of there, right? So maybe minus b hat 1, I guess it doesn't matter, but we'll just leave it like that, equals 0. Now, I want to solve for b hat 1, right? So I'm just going to take my b hat 1 guys, and I'm going to pull them over here. And let's do that. Let's see what we get. 1 over n, the sum of my xi, yi's, minus 1 over n, the sum of my x. Well, okay, listen, let's think about this. The sum of my xi, y bar could be pulled out of here, and 1 over n, sum of my xi, that's just x bar, right? So really, isn't this the same thing as x bar, y bar? I think it is, okay? And then that's going to be equal to pulling these guys over here. Let's see, that's going to be b hat 1, and let me just pull that out, and we'll see what we have. We have 1 over n, sum of my xi squareds, and then minus 1 over n, and this is the sum of my xi, x bar, b hat 1. Again, b hat 1 and x bar don't depend. I pulled out b hat 1. X bar, though, like that could be pulled out of the sum. So I have 1 over n, sum of my xi's again, and that's just going to give me x bar again, isn't it? So 1 over n, sum of my xi's is x bar times x bar. So that's going to be x bar. All right, equals, oh, no. Don't need to equal 0. So now let's just solve for b hat 1, okay? B hat 1 is going to give me some kind of 1 over n, sum of my xi, yi's, minus x bar, y bar. Oh, I kept this 1 over n in here. I shouldn't have. 1 over n, sum of my, where did I pull this from? 1 over n, sum of my xi's is x bar. So that 1 over n disappeared. It's x bar. That's just what it is. So I have this over 1 over n, sum of my xi squareds, minus x bar. Huh, interesting. So this kind of, this looks like expected xy minus expected x, expected y. Isn't that a covariance formula? And then got expected x squared minus expected x, expected x. That sounds like a variance formula. Oh my gosh. Well, this is literally just the covariance of xy over the variance of x. All right, well, it's kind of crazy, huh? It's cool how that worked out like that. All right, well, there you go. That's your OLS estimators, b hat 1, b hat not. Not too crazy. Let's see what else we got in the chamber. All right, what's up next? Well, we have OLS, but there is that problem with OLS where we could have omitted variable bias. Okay, so let's say that we have a situation where our true model is going to be yi, and I'm going to drop the i's actually here right now, but y equals beta naught plus beta 1x, right? That's what we're measuring, plus epsilon and everything. But the true model actually has beta 2 w, right? W is some omitted variable plus nu, right? Do I want to call that nu? I'll call it eta. It really doesn't matter, but I'll call it eta here. So this is the true model, but what we're estimating is beta naught plus beta 1x plus epsilon, right? This right here, this would be our epsilon, and we'd have an omitted variable in there. So what would happen in that case when we tried to estimate that beta hat 1 that we just got? Well, that would give us the covariance of xy over the variance of x. Let's plug these bad boys in. So the covariance of x and y would be the covariance of x and y's true value is beta naught plus beta 1x plus beta 2w plus eta. And that's going to be, of course, over the variance of x. Now, this would be equal to, well, the covariance of x and beta naught's a constant, so that's going to be 0. All right, so we don't have to worry about that. Covariance of x and x, we can pull beta 1 out. So that's beta 1 covariance of x and x, which is just the variance of x. Okay, fair enough. And then beta 2, pull that out, covariance of x and w. Covariance of x and w. And then, you know, covariance plus the covariance of x and eta. Well, we're going to assume that this is the true model. In the true model, that exogeneity does hold with eta and x. So that can go to 0. All right, but this is all over the variance of x. So what this leaves us with is actually, all right, that's just beta 1. So that would be great if it was just beta 1. That would mean that it was unbiased, right? Oh, you know, this is actually my bad because I should have written that beta hat 1. Actually, it's technically the sample covariance of x and y over the sample variance of x. Yeah, so we're showing what it converges to. As n goes to infinity, that converges to covariance over variance. There you go. Yeah, keep that in there. So it should be beta 1, but we actually have this beta 2 covariance of x and w over the variance of x. All right, so that's not good. This is omitted variables bias right there. Shoot, well, I mean, this wouldn't be omitted variables bias if beta 2 was 0 or covariance of x and w was 0. I mean, clearly, right? Like, for something to be an omitted variable, the omitted variable has to be correlated with x, check, and with y, right? Beta 2, w has an effect on y. So, but right here, if neither of those things, or both of those things are non-zero, then you got omitted variables bias. That is a problem. So the sign of these two things, when you multiply them together, that will determine the direction of your omitted variables bias, okay? That is a problem. That is a problem with OLS. Okay, I know how to solve this. We go to multiple regression. Let's do it. Let's take our OLS estimators and let's just make them multiple, okay? Let's go to multiple land for them. All right, so we got matrix aversion. Let's do the same thing. Let's minimize the sum of our squared residuals. Our residuals is a vector. Vector? Yeah, it's a vector. U hat, right? U hat is our vector of residuals. And so it would actually be U hat transpose U hat. What we're minimizing, that's it's squared. You know, that's how you square something in matrix land. We're going to choose our B vector to minimize the sum of our squared residuals. So just to make sure we're good on this. So our residual is going to be y minus y hat. And y hat is going to be, you know, xb. Okay? Y minus xb. Okay? So this is transpose. Y minus xb transpose, y minus xb is what we're minimizing. Okay? So, okay, before we take our derivatives and go crazy with that, let's just try to simplify this, or multiply it out, I should say. Or not even multiply, just transpose it. So y minus x beta, the quantity transposed, is just going to be y transpose, right? Minus xb, well, okay, xb transpose is going to be b transpose x transpose. And then it's that multiplied by y minus xb. We actually can multiply this. Let's FOIL it, okay? We can just FOIL this bad boy. So that's going to be what? Y transpose y minus y transpose xb minus b transpose x transpose y plus b transpose xb. Interesting. Okay, now let's take our derivative. And we're taking our derivative with respect to b. Now pause. Okay, this is the part where a lot of people get tripped up. So I'm going to say something real simple here. I'm going to break this down. What are the dimensions of y? Y, if you remember, is an n by 1 vector, right? So we got an n by, so y transpose would be 1 by n. Okay, so we got a 1 by n here times an n by 1. Well, that's just a 1 by 1, yeah? Okay, let's see what this is. Y transpose is 1 by n. X is, what is that? That's an n by k plus 1, isn't that? N by k plus 1. And then b, well, that's just a vector. That's just a k plus 1 by 1, right? k plus 1 by 1. Wait a second. So this is a 1 by 1. And that's a 1 by 1. What the heck is this? This is that's a 1 by k plus 1. That's a x transpose. What is that? That's a k plus 1 by n. And then y is an n by 1? That's just a 1 by 1. Okay, what about this one? What about this one? Let's say b is a k plus 1 by 1. So b transpose is 1 by k plus 1, and x transpose is k plus 1 by n, and n by k plus 1, and then a k plus 1 by 1. Wait a minute. All of these are 1 by 1s. Essentially, you got a scalar minus a scalar. This whole thing is a scalar. So we're taking the derivative of a scalar, of just like a regular number with respect to a vector. What does that mean? Well, basically it means that in our vector of b's, right, b0, b1, b2, all those bad boys, we're saying, what is the change in this with respect to each of these bad boys? And in order to answer that question, we're actually going to end up with a vector, or we're going to end up with something with these dimensions right here. Okay, so that is kind of our rule that we're going with. Let me put this down a little bit. When we take our derivative with respect to b, we are going to get a vector with the dimensions of b. All right, now I say that because of this. If I take my derivative and, okay, it's with respect to b, okay, is there a b in y transpose y? No, okay, so I don't touch that. That just disappears. Is there a b in y transpose x? Yes. So I might write negative y transpose x. This is something that somebody could potentially do, maybe has done when they're doing this. And what is y transpose x? Well, y transpose, wait a minute, is a 1 by n, and then x, as we've established, is an n by k plus 1, right? Okay, well, that gives us a 1 by k plus 1. All right, but we're, aren't we looking for a k plus 1 by 1? All right, so immediately, I know that I've done something a little fishy, okay? So to follow my golden rule, right, I can't have y transpose x. All right, when I take my derivative with respect to b, it's gotta be x transpose y. I gotta transpose this bad boy so that it's in a form I can work with. What's x transpose? That is, let's see, that's a k plus 1 by n, and that's an n by 1. Okay, that gives me a k plus 1 by 1. All right, so we're chilling because a k plus 1 by 1 is what I want to end with. All right, so I got negative x transpose y, and then what is this? Again, minus x transpose y. There's a b in it. I get it's on the other side, but I need it in the right dimensions. Okay, so I got negative x transpose y minus x transpose y plus, and then this has got two b's, so it's kind of like it's a b squared right there, right? So I'm gonna act like it's a squared. I'm gonna pull that 2 down, kind of like we did before. So it's a 2, and then what if I said x transpose x b? Is that the right dimensions? Well, x transpose, let's see, that is a k plus 1 by n. This is an n by k plus 1. That's a k plus 1 by 1. So I get a k plus 1 by 1. We're good. We're chilling. We're chilling. K plus 1 by 1 the whole time. Okay, that equals 0. Now I feel pretty confident that I can solve this and everything's going to be all chili beans. Okay, so that means that, let's see, 2x transpose x b equals 2x transpose y. Kill those 2's there. Solve for b. Okay, so that's going to mean that b equals, put this in the front, x transpose x inverse, because that's how you divide in matrix land, and then x transpose y. Boom, and this is our beta hat. I should have put it on there from the beginning. We set it equal to 0. Okay, all right, so it's not too bad, not too bad. A little funky matrix stuff going on, but that's essentially how you do that. And it's pretty good for not really knowing any matrix algebra before this class. All right, well, let's see, what else we got? We got our OLS estimators. Let's make sure those are unbiased, actually. I just really want to make sure when we're in matrix land that we're still doing unbiased stuff. So let's take the expected beta hat, which is our new favorite vector, given x. What's expected beta hat given x? Well, we just found beta hat, right? Let's see if I can remember it. Beta hat is x transpose x inverse x transpose y. And let's plug y in too. So y, we know, is x b plus epsilon, right? Well, x beta plus epsilon is our true y. Okay, so X transpose X inverse, X transpose XB plus epsilon. Fair enough. All right. Now I'll make it a B. You know, you can make it a B, make it a beta. I kind of like making it a B. Anyway, given X. All right, it's expected all of that given X. So let's do our expectation here. Let's just multiply this out really quick. I'll keep the expectation out here. This is X transpose X inverse X transpose XB plus X transpose X inverse X transpose epsilon, right? Did I multiply that right? Given X. Now, wait a minute. X transpose X inverse X transpose X, that's an inverse times the thing it's inversing. That just goes to the identity matrix, doesn't it? So that just leaves us with B. So let's simplify that. Expected B plus X transpose X inverse X transpose epsilon given X. And given X means that we can treat X as a constant. So we get, let me put this expectation out, we got expected B plus, and we got, let's see, treating X as a constant. So I'll pull that out of my expectation operator and get X transpose X inverse X transpose expected epsilon given X. Holy cow, wait, expected epsilon given X, don't we assume that's 0? Yeah, that's exogeneity right there. Now this whole thing's going to be 0 then. Wait, it's just expected B. That's beta. All right, cool. Sounds like it's unbiased. Works for me. Okay, now that we know it's unbiased and we're sure of that, let's do some inference. In order for us to do our multiple inference, we got to know the variance. We got to know the variance of B hat. Okay, what is the variance of B hat given X? Well, oh shoot, I shouldn't have erased that. I just have to plug all this stuff in again. Okay, this is the variance of X transpose X inverse X transpose X B plus epsilon given X. Okay, boop. Just like that. All right, which is equal to the variance of, we've done this before, X transpose X inverse X transpose X B. That's all going to be the identity matrix. And we're just left with B plus X transpose X inverse X transpose epsilon given X. All right, did I do that right? So that's going to be equal to the variance of B plus X transpose X inverse X transpose epsilon given X. How do I do this now? Well, I guess the variance of two things. Let's see. Oh, well, this is great. The variance of B is just, B or our beta is just like a true value, right? Maybe I should have put beta in here. Beta is a true value, so it's not going to vary. So we're just going to have our variance of X transpose X inverse X transpose epsilon given X. And again, given X means we treat X as a constant, right? So when we pull a constant out of a variance, we can do that. We just got to square it. Okay, so let's square that bad boy. So we have X transpose X inverse X transpose, and then we got our variance of epsilon. And then let's put this on the other side and transpose it. That's how you square things in matrix land. So we got, what's that transpose? It's going to be X, and then X transpose X inverse is just its own transpose. So we're good. All right. So variance of epsilon, by homoscedasticity, don't we assume that that's sigma squared? So we can just call that's just a number. That's just a scalar right there. Sigma squared, well, a sigma squared I guess technically, we got a matrix of diagonals, but I, we don't care about the I, and sigma squared is literally just a number. So we'll pull the sigma out here, right? Sigma squared X transpose X inverse X transpose X, X transpose X inverse. Whoa, okay. Well, pick your favorite. That just goes the identity matrix, right? So we're left with sigma squared X transpose X inverse. All right. I feel like that is a win. We'll keep it. So that's the variance of your good old OLS estimator in matrix land. Now, the thing is that there's so many problems with OLS, right? There's so many things that can go wrong. One of those things is reverse causality. Okay, so let's say you have Y And, it depends on x. You got beta naught plus beta 1 x plus epsilon. But x also depends on y, right? So if you got that, you got x equals alpha naught plus alpha 1 y plus nu. Okay, so that's not encouraging. So what do you get from that? Like, let's talk about exogeneity, right? Because we assume that the covariance of x and epsilon is 0. But what is the covariance of x and epsilon if you have reverse causality? Well, let's take a look, right? Let's see what we got here. So that's going to be the covariance of, let me just plug this in, beta naught, x is the alphas. So that's going to be alpha naught plus alpha 1 y plus nu and epsilon. Let me clean this up. That's going to be the covariance of, well, alpha naught and epsilon. Alpha naught's a constant, so that doesn't vary. So it's just alpha 1 covariance of y and epsilon plus the covariance of nu and epsilon. And under these assumptions, let's just assume that these, covariance of those is 0. All right, that's a lot of times given when we're discussing reverse causality. So, okay, we're almost there. Alpha 1 covariance, let's plug in y. That's going to be beta naught plus beta 1 x plus epsilon and epsilon. Now that's going to equal, let's beta naught, epsilon. They don't covary. All right, so alpha 1 covariance, so that's going to be alpha 1 beta 1. Interesting. Covariance of x and epsilon plus, what is that? The covariance of epsilon and epsilon? That's just the variance of epsilon, right? Well, now we got the covariance of x and epsilon on both sides. It seems like we're right back where we started, All right, let's just solve for this bad boy instead of plugging it in again. So we'll subtract them over here. So that will give me what? 1 minus alpha 1 beta 1. And that's going to be times the covariance of x and epsilon. And that is going to be equal to the variance of epsilon. Am I right? Shoot, I don't feel like I'm right. Oh, I left my alpha 1 out here. Alpha 1 covariance times this plus alpha 1 variance of epsilon. Yeah, slipped away from me there. Plus alpha 1 variance of epsilon. So that means that we're going to end up solving for the covariance of x and epsilon with alpha 1 variance of epsilon over 1 minus alpha 1 beta 1. Well, shoot, that doesn't look like 0, does it? I mean, I guess it could be 0. The variance of epsilon, it's probably not going to be 0. But so if alpha 1 was 0, then, that could be, well, shoot, yeah, obviously. If x does not depend on y, essentially, AKA if there's no reverse causality. I could have told you that. I need a proof for that. You kidding me? Get this out of here. All right, let's do something else. Let's do, another problem with OLS, right? Measurement error. That is definitely another thing that can happen. Okay, so when you got measurement error, basically, you got your true model, which is y equals, let's say, beta naught plus beta 1, and you got your true x, right? It's xt, we'll call that your true x plus epsilon. But fact of the matter is people are reporting stuff wrong. Dang it. And so your x that you measure is your true x plus some error nu. Okay? And we're gonna make a couple assumptions here. First of all, we will assume exogeneity at least between the true x and epsilon. All right, we're continuing to assume that here. We're going to assume that the covariance of epsilon and nu, we're gonna say that that's 0, right? And we're also going to say that the covariance between our true x and nu is 0. Okay, is that pretty fair? So we got this is a case of classical measurement error. Okay, and classical measurement error is basically just measurement error where your misreporting is truly random, right? It is not correlated with your x's. It's just everyone's just randomly misreporting, which is if you have if you have measurement error that is correlated with your x's, then that's even worse. Okay, we're not even going to talk about that. We're not even going to touch that. We're just going to talk about classical measurement error right now. So what does that mean? Okay, let's all right, let's try to do OLS again. So our beta hat 1 is going to be our covariance of x and y over our variance of x. These are sample variances. As n goes to infinity, that should converge to the covariance of x and y over the variance of x. Okay, so in this case, let's plug in for the covariance of x and y. Well, what do I want to do first? I'll do, I guess, y. So this is going to be the covariance of, let's see, the covariance of x and beta naught plus beta 1 x true plus epsilon and, whoa, oh, nope, that's it. That's what we got over the variance of x. Okay, let me try to clean this up. So that's going to be the covariance of x and epsilon. Ooh, so that's the covariance of, and what is x? It's the true x plus nu. So covariance of true x plus nu and epsilon plus, all right, beta naught and, oh, why did I do epsilon first? That was kind of a interesting choice. Okay, so it's the covariance of x and beta naught, those don't covary. Covariance of x and epsilon, which I just did for some reason. Then the covariance of x and b1 x true. So this is going to be the covariance of x true plus nu and b1. I'll just pull the b1 out. b1 covariance of x true plus nu and x true. This is looking a little bit sloppy over the variance of x true plus nu. All right, so I plugged in for x after plugging in for y. And okay, let's see if we can simplify this now. So this is going to be the covariance of x true and epsilon. All right, we got exogeneity, that's 0. The covariance of nu and epsilon. All right, we assume that that's 0. Okay, so actually this whole thing can go to 0. We're fine there. Then we have the beta 1 covariance of x true and x true. So me beta 1 variance of x true. Okay, and then the covariance of nu and x true. Oh, that's 0. Okay, that's perfect. Okay, so really on the top we just got beta 1 variance of x true. We're looking pretty good. And then, but this right here, shoot, what's that going to be? Well, I guess it's the variance of x true plus the variance of nu plus 2 times the covariance of x true and nu. Okay, well. Those don't covary, so that's going to be 0. But now, okay, well now look at this. We're left with this. So we should have just beta 1, and instead we end up with beta 1. We can't even. It's beta 1 times some weird thing. We got the variance of x true over the variance of x true plus the variance of nu. All right. Well, here's the problem with this, is that this numerator is going to be less than this denominator. Variances are always positive, right? So, well, shoot. What that means is that this is going to be multiplying beta 1 by something that's less than 1. So I think that's called attenuation bias, all right? Or basically, you're attenuating your coefficient towards 0, your bias towards 0. It's not good. Not very good at all, okay? Measurement error, not a good place to be in. All right, well, maybe OLS is not the way to go. Maybe instead of OLS, we can get a little more creative. Let's do IVs, huh? What about IVs? Now, I don't think IVs are biased, or unbiased, rather. They actually, I think they are biased, but they are consistent, right? I'll show you those bad boys are consistent. Your beta hat IV is going to be obviously your sample covariance of z and y over your variance of over your covariance sample of z and x. And let me show you that bad boy is consistent, right? Did I just drop a lid? Oh, I guess he's gone. Okay, so that as n goes to infinity, that bad boy should converge to the covariance of z and y over the covariance of z and x. So that's going to be the covariance of z and beta naught plus, we didn't define y, but let's say it's beta naught plus beta 1x plus epsilon. And let's say that's over the covariance of z and x. Okay, so that's going to equal, beta, again, z and beta naught don't covary. We don't have to worry about that. Covariance, so b1 covariance of z and x plus covariance of z and epsilon. But we do assume exogeneity. Remember that z and epsilon do not covary. We assume relevance, so z and x definitely covary. Z and epsilon, nah, we got a good instrument. So if you got a good instrument, this is going to be over the covariance of z and x. And look at that. Those cancel out, and we get beta 1. Looks like IVs are pretty solid, pretty good. All right, well, now we got IV consistency, but what if we are over-identified and we find out we have to use two-stage least squares? Actually, you know what? Here's what I'm going to do. I'm going to show you that 2SLS, when you're just identified, actually will collapse to your just identified case. Remember, we said beta hat when you're just identified is going to be, what did we say? Z transpose X inverse Z transpose Y? Something like that. Well, I'm going to show you that two-stage least squares, when you're just identified, will collapse just to that one special case, okay? How do you do two-stage least squares? Let me see. You regress. Let me see if I can remember. You regress your X on your Z, right? Yeah. You regress your X on Z, right? Oh, and then you get your predicted values, and then you're going to regress your Y on those predicted values. Yeah, I think that's good. Okay, so how does that end up? So if we have beta hat, call this beta hat Z. So from this first stage, our first stage is going to give us a beta hat of Z transpose Z inverse Z transpose X. Okay, yeah, that's beta hat if you were to regress X on Z. I think that's pretty plausible. So your predicted values then would be, well, let's see, your X hat predicted values would be Z beta hat Z, right? Like Y equals X beta, but or Y equals X B hat, but we're just plugging this in for our regression. So that means that would equal Z times Z transpose Z inverse Z transpose X. And you didn't cover this. You call this part right here, this is called the projection matrix. Really, your predicted values is just your projection matrix times X. I'm just going to leave that placeholder in there so I don't have to write Z 4 times for this next part, because I would have to write Z a lot. So that's your first stage, right? You get your predicted values, and now you're going to regress Y on X. Well, if we regress Y on X, then our beta hat from that regression is going to be what? Beta hat is going to be X hat transpose X hat inverse X hat transpose Y. Am I right about that? I think I am. Okay, so let's plug in for our X hat. All right, this might be a little dicey. This is going to be, okay, so let's call this PZX. So we'll call this PZX transpose, and let's just transpose it right now. PZX transpose is X transpose PZ transpose, and then X hat we called PZX, and this is that inverse, and then X hat transpose again is PZX transpose is X transpose PZ transpose. Am I doing that right? X hat transpose is X transpose PZ transpose, yeah? And then Y. And what did we define Y as? Do we want to, let's just leave Y. I think we just leave Y right now. So that's what we end up with. So here's the thing. We're going to note that PZ, the projection matrix, is actually symmetric and idempotent. Remember, symmetric means that its transpose is itself, and idempotent means that if you were to multiply it by itself, then you would just get itself. Okay, so, or, that doesn't have to be transpose, right? So it's symmetric and idempotent. So what that means is we can simplify just this bad boy right here to just 1 PZ. That might make our lives a little bit easier. Okay, so what do we do now? Well, let's talk about just identified. If we're in a just identified case, then this right here, we're going to realize that just identified means that Z transpose X, if you have just as many instruments as you have endogenous regressors, then Z transpose X is going to be square and it's going to be invertible as well. Okay, that's what happens when you're just identified. So then if Z transpose X is square and invertible, what you're going to end up with is this. And let me put my Z's back in here so we can see what's going on. My X transpose, I'm going to put PZ back. That's going to be Z transpose Z inverse Z transpose X inverse, am I doing that right? X transpose PZ transpose, which is this whole thing transpose. So let me just do Z. Oh, isn't that the same thing? Z transpose Z inverse Z transpose. Am I missing something? PZ Y. Okay, Y. I feel like I did that right. I'm hoping I did that right. Okay. So when I take the inverse of this, let me take the inverse of this giant thing. So I'm going to flip these things, and I'm going to get what? I'm going to get, what does that even say? I didn't even read my own writing. I think that says Z transpose X. So the inverse would be, this is going to be, yes. Z transpose X inverse, Z transpose Z inverse stays in the middle, and then X transpose, X transpose, yeah, no, I'm second guessing myself. It's X transpose Z inverse, okay? Times X transpose Z, Z transpose Z inverse Z transpose Y. Holy cow. No, I didn't inverse my inverse. Dang it. Yeah, that's going to be inversed right there. What does that leave us with? Well, X transpose Z inverse X transpose Z is going to be the identity matrix. And then we're going to have Z transpose Z, Z transpose Z inverse. That's the identity matrix. So we end up with Z transpose X inverse Z transpose Y. And that, my friends, is the same as your just identified case for IV. Okay, well, that's all the proofs that I know of, at least. So I don't even know what to say to that. Guess we're done.